Have you ever really stopped to think about the journey a piece of metal takes? It is an absolutely incredible process, one that starts with, a simple chunk of rock and ends up as the very materials that build our entire world. So today, we're going to dig deep and uncover that secret life of metals.
I mean, think about it. That shiny, super lightweight can in your hand, it's something we use every single day without a second thought. But it began its life as this humble, earthy rock called bauxite. So how in the world do we get from that to this? Well, that's the big secret we are unlocking today. Okay, so the very first step is basically a global treasure hunt. But here's the thing. We're not just looking for any old rock. We need to find these specific rocks that are just packed with the metals we want. And this is where we have to know the difference between a simple mineral and a really valuable ore. So, what is the difference? Well, think of it this way. All ores are minerals, but not all minerals get to be called ores. A rock only earns that special title ore if it has enough valuable metal inside to make it actually profitable to mine. See, it's not just about what's in the rock. It's about whether it makes economic sense to go through all the trouble of getting it out. And here are some of the star players in the world of ores. Bauxite, that's what gives us our aluminum. Hematite is the main source of iron for all our steel. And you've got both zinc blende and calamine, which are key for getting zinc. These are the real treasure rocks that power pretty much all of our industries. So, once we have our ore, how do we get the metal out? Well, the science of doing this has a name. It's called metallurgy. And you can basically think of it as a giant high-tech recipe. Let's take a look at the 4 main steps that make up the blueprint for this whole process. It's a really logical flow when you see it laid out. First, you have to clean the ore. Second, you convert it into a form that's easier to work with, which is usually an oxide. Third, you finally separate out the raw metal, and last but not least, you refine it to perfection. All right, let's break down those first 2 prep steps. So yeah, these first 2 steps are all about preparation. You can't just toss a dirty rock into a furnace and expect a perfect piece of metal to pop out, right? First, you've got to clean it up, and then you have to give it a good cook. Now, there's a technical term for all that unwanted dirt, sand, and rock that's mixed in with our precious ore. It's called gangue. A good way to think about it is like the mud you have to wash off potatoes before you can even think about cooking them. Getting rid of the gangue, that's the whole goal of concentration. So how do we clean it? Well, for sulfide ores, there's this incredibly clever method called froth flotation. It works by mixing the crushed up ore with water and oil. And here's the really cool part. The metal particles, they love to cling to the oil, while all the unwanted rock and dirt, the gangue, prefers the water. So when you bubble air through this whole mixture, the oily, metal-rich froth floats right to the top, where you can just skim it off. It's a simple but absolutely brilliant way to separate everything. Next up is the cooking phase, where we convert that clean ore into a metal oxide. And there are 2 main recipes here, roasting and calcination. The key difference between them is air. For sulfide ores, you use roasting, which means heating them with plenty of air. But for carbonate ores, you use calcination, heating them with no air at all. So even though the methods are different, the goal is exactly the same. Turn it into a metal oxide. Okay, we've cleaned it, we've cooked it into an oxide. Now it's time for the main event, getting the pure metal out. This step is called reduction. And the method we choose depends entirely on the metal's personality, which is all laid out for us in a kind of chemical rulebook. This really is the million-dollar question in metallurgy. Do we just heat it up? Do we need to add another chemical to the mix? Or do we need to bring out the big guns, like a massive jolt of electricity? The answer to that is found in something called the reactivity series. And here it is. This chart is basically a chemist's cheat sheet. It ranks metals from the most reactive at the top, like potassium, all the way down to the least reactive at the bottom, like gold. A metal's position on this list tells you everything about how hard it's going to be to extract. The higher up it is, the more stubbornly it holds on to other elements, because those chemical bonds are just so much stronger. It means we need a lot more energy to pry it free. And that rule book gives us a crystal clear answer. For metals at the very top, like aluminum, they're so reactive they need the brute force of electrolysis, which is literally using electricity to rip them apart from their oxides. Metals in the middle, like iron and zinc, they can be persuaded to let go using carbon, usually in the form of coke. And those super unreactive metals at the bottom, like gold, well, they're often found nearly pure already.
All right, now that we have the theory down, let's see it all in action with a metal we all know and use constantly, aluminum. Remember that soda can? Let's trace its journey from a bauxite rock all the way to a finished product. But first, a little bit of context here. It might actually surprise you to learn that aluminum is the most common metal in the Earth's crust. It is literally everywhere. But because it's so high up on that reactivity series, getting it out of the ground was incredibly difficult for a very, very long time. So the first stage is all about purifying the bauxite ore. This is called the Bayer's process. We use a hot solution of caustic soda to dissolve the aluminum compounds, which leaves all the impurities, like iron oxide and sand, behind as this waste product called red mud. After a few more steps of cooling and then some really intense heating, we're left with this fine white powder, pure alumina, also known as aluminum oxide. Now for the main event, the extraction. Because aluminum is so reactive, we need to use electrolysis. This is the Hall-Héroult process. That pure alumina powder is dissolved in molten cryolite, and then we just blast it with a massive electric current. This jolt of electricity is strong enough to finally break that super tight bond between the aluminum and oxygen, releasing pure, liquid aluminum metal. Let's take a look inside one of these industrial cells. What's happening is we're passing a really powerful current from a positive terminal, the anode, to a negative one, the cathode. As that electricity flows through the molten mixture, it attracts the positive aluminum ions over to the negative cathode. When they meet, they become pure liquid aluminum, which is heavier, so it just pools at the bottom, all ready to be collected. But this whole process needs some really crucial helpers to even work. You see, alumina's melting point is over 2,000 degrees Celsius, which is insanely hot. But by adding cryolite, it drops that temperature all the way down to a much more manageable 950 degrees. That saves a massive amount of energy. Then, fluorspar is added to help everything dissolve and conduct electricity better. And that layer of powdered coke on top, it's basically like a blanket, insulating the whole system to keep the precious heat in. So we have our pure metal. Awesome. But, a lot of the time, pure metals aren't quite strong enough or durable enough for what we really need them for. And that's when we start mixing to create materials with what you could almost call superpower-like properties. And that is exactly what an alloy is. It's a custom-made material. It's a recipe where we mix metals together, or a metal and a non-metal, to get the best of all worlds. We're enhancing things like strength, or lightness, or resistance to rust. And you know these alloys really well. Bronze, one of the first alloys ever made by humans, that's a mix of copper and tin. Stainless steel gets its amazing rust-proof quality from adding chromium and nickel to iron. And duralumin, which is a super strong yet very light aluminum alloy, well, that's what we use to build airplanes. So we've seen the incredible science and industry that it takes to get these materials from the Earth. Every single step requires massive amounts of energy and resources. And it really leaves us with a critical question to think about. As we continue to build our modern world, how do we do it sustainably?